Hey everyone, Mr. Hauk here. In today's video, we're going to learn how to represent and solve systems of linear equations using matrices. Let's go ahead and get started. So consider the system right here. It has three variables, x, y, and z, that we would want to solve for. We know from algebra that we can use substitution and elimination to solve the system for x, y, and z. It turns out we can also use matrices to solve this system. First, we're going to need to discuss how to represent systems of linear equations using matrices, and then we'll discuss how to solve those systems using matrices. So first, let's look at how we can write systems as matrices. Again, consider the system that we had previously. In order to write this system as a matrix, we're going to take the system and split it into three different matrices. We're going to have something called the coefficient matrix, the variable matrix, and the constant matrix. Notice that the coefficient matrix is just a matrix of all the coefficients of the variables. So look at the first row right here. Let me use a highlighter here. Look at the first row in the coefficient matrix A, 1, negative 4, 3. Now look at the first equation of the system. The coefficients of the variables are 1, negative 4, and 3, and notice that they're in order x, y, z. So in our coefficient matrix, they're in the correct order, x, y, z, and they're just the coefficients. Notice that in the second row, our coefficient matrix is negative 1, 3, negative 1, and very similar over here in our second equation in the system, our coefficients are negative 1, 3, and negative 1, once again in order, x, y, z. In the third row, our coefficients are 2, 0, negative 4. And this one we have to pay special attention to, because notice that in the third system, or the third equation in the system, the coefficient of x is 2, but notice that we don't have a y, and the y is supposed to be in between x and z, so we would say that that's a 0y, even though it's not written there. So we know that in our coefficient matrix, we're going to have a 0 for the coefficient of y. And then, of course, we have negative 4 as the coefficient of z. So again, we call this the coefficient matrix X. Then we have our variable matrix X right here. I think I misspoke earlier, coefficient matrix A. We have the variable matrix X. This is the matrix of unknown variables that we're trying to solve for. And then we also have the constant matrix B. And notice that in our systems of equations, on the right side of each equation are the constants 5, negative 3, and 6. That's where our constant matrix is coming from. So when we want to take a system and write it as a matrix equation, we need to make sure that first, all of the equations in the system are written in the correct order, with the variables on the left going x, y, z, or a, b, c, however you want to order the variables. The variable matrix is going in the correct order, so this was going x, y, z, so our variable matrix has to go x, y, z as well. And then on the right side of each equation, we need to have our constants separated from the variables. That way we can have the correct constant matrix. Okay, let's look at a couple quick examples here. In our first example, we want to write the system below as a matrix equation, ax equals b. We want to identify the coefficient matrix, the variable matrix, and the constant matrix. So let's do the coefficient matrix first. Notice that the variables here are a, b, and c in that order. And notice that in the first equation, there is no a. So this would be a 0a. So our coefficient matrix for the first row is going to have a 0, a negative 1, and a 2. The second row for the second equation in the system, the coefficients are 1, 1, negative 1. And the third row, our coefficients are 2, 0, and 3. And once again, notice in the third equation, there is no b variable, so that'd be like a 0b, which is where the 0 was coming from. Okay, now we're going to go ahead and write the variable matrix. Well, looking at the variables, they're a, b, and c in that order, so let's write them as a, b, and c. And then last, let's look at our constant matrix. Each one of these equations in the system already had the constants separated from the variables. Our constants are 4, 0, and 11. They're on the right side of the equal sign. So our constant matrix is 4, 0, 11. And this is our matrix equation, AX equals B. Notice that this right here, again, this is our coefficient matrix. And that's A. Here's our variable matrix. And that's X. And here's our constant matrix. Which is B. So altogether, AX, A times X equals B. Okay? In our second example, when asked to represent the following equations as a matrix equation, a student produced the following. Will the student's answer, or will the student's equation, result in a correct answer? Justify your answer. Well, let's look at it here. Let's start by trying to figure out if the student's coefficient matrix is correct. So the coefficients should go 7, -1, +1. But their coefficient matrix for the first row goes 7, 2, 4. So right off the bat, we're going to say no. Their answer, or their equation, their matrix equation, would not result in a correct answer. The reason being, their coefficient matrix is not set up correctly. Okay, so that'd be my justification. The coefficient matrix is not set up correctly. Okay, instead, here's what the coefficient matrix should look like. It should be 7, -1, 1 for the first row. For the second row, it should be 2, 2, -3. And for the third row, it should be 4, 1, 5. Okay, that's what the correct coefficient matrix would be. Notice that their variable matrix is fine, x, y, z. That's the correct order of the variables. And notice that their constant matrix is also fine because the constants in the system have already been moved to the other side of the equation to -3 and 6. Okay, so only their coefficient matrix needs to be adjusted. So now that we know how to represent systems with matrices, let's talk about how we could solve systems with matrices. And before we do that, let's take a quick look or a quick reminder on multiplicative inverses. So let's use multiplicative inverses to solve this very simple algebraic equation. We have the equation 3x equals -27. Remember that a multiplicative inverse is where you multiply two numbers together and we get a 1. So what number would I multiply by 3 to get a 1? Well, the answer is 1/3. So what we're going to do is we're going to multiply both sides of this equation by 1/3. Okay, so 1/3 times 3x equals 1/3 times -27. Notice that on the left side of the equation, 1/3 times 3 gives me a 1. We're left with just x equals, and then 1/3 times -27 would be -9. So using the multiplicative inverse of 3, we're very easily able to calculate what x should be. The same logic is going to hold true for solving matrix equations. So let's take a look right here. This is our generic matrix equation, A times x equals B. Remember that A is a coefficient matrix, X is a variable matrix, and B is a constant matrix. Our goal is we want to solve for the coefficient matrix X, because our coefficients, or sorry, not the coefficient matrix, this should actually say, so this is actually a typo. Let's correct this typo real quick. This should not say coefficient matrix X, this should say variable matrix X, because we're trying to solve for the unknown variables. All right, so small typo, let's fix that. But let's use the same logic. If I want to solve for the variable matrix x, then I can multiply both sides of this equation by the inverse of A. So here's what we would do. A inverse on both sides. So A inverse times AX equals A inverse times B. So multiplying both sides of this equation on the left side by A inverse. And it's important that it's on the left side because remember that for matrices, matrix multiplication is not commutative. We showed that in a previous video, meaning that you can't just simply multiply in any order that you want. So we need to make sure that since we multiply it on the left side here on the left, that we also multiply on the left side here on the right side of the equation. Well, we saw previously that when you take an inverse, when you multiply a matrix times its inverse, you get an identity matrix. So this will give us the identity matrix I times X is equal to A inverse times B. But we also know that anytime we multiply an identity matrix to another matrix, we are simply left with that matrix. So this will be X equals A inverse times B. And notice that we have achieved our goal. We wanted to solve for the variable matrix X, and the variable matrix X is simply A inverse times B, where A inverse is being multiplied on the left side. Very important there. So let's see an example, and there's going to be a lot of work that goes into this example, so make sure to follow along here. Let's use this concept of multiplicative inverses to solve a system of equations represented as a matrix equation. First, let's rewrite our system in standard form, meaning we want our variables on the left in the correct order, x first, then y, and we want our constants on the right side of the equation. So that's how we're going to start here. I'm going to go ahead and make a little bit of space on the right side. This is where I'm going to rewrite the system. Okay, so I'm going to title this Rewrite System, and let's do a little bit of work. All right, so the original system, y equals negative 2/3 x minus 17/3, and then y equals x minus 4. Well, we want our variables on the left side, we want our constants on the right side, and I also want to have the x's first and the y's second. So I'm going to take this negative 2/3 x, I'm going to add it to the other side of the equation. This is going to give us 2/3 x plus y equals negative 17/3. And same thing in our second equation, I'm going to take this positive x, subtract it over here. This will give us negative x plus y equals negative 4. Now, technically speaking, this is perfectly fine to work with. It's set up in the correct order, x, y, with the constants on the right side. However, most students would have a hard time working with the 2/3 and the negative 17/3. So one thing that I can actually do is multiply every term in this top equation by a positive 3. That way I can get rid of the fractions. So an easier system to work with after multiplying this entire equation, top equation, by 3 would be as follows. We would have 2x plus 3y equals negative 17. And in the bottom equation of the system, there's nothing we need to worry about. We're going to keep it as negative x plus y equals negative 4. Okay? So this is our system rewritten so that it's easier to write our matrix equations. So let's go ahead and write our matrix equation, starting with the coefficient matrix, 2, 3, negative 1, 1. Now let's write our variable matrix. Well, we know that we're going in the order x then y, so our variable matrix will be xy equals, and then we'll write our constant matrix, which is negative 17, negative 4. Again, this is A times B. Sorry, not B, that should be X. My mistake. A times X equals B. There we go. And again, remember that our goal here, is to solve for the variable matrix X. Well, we know from up here that the variable matrix X is A inverse times B. So X equals A inverse times B. So one of the things we now need to worry about is calculating A inverse, and we discussed how to do this in a previous video, so I'm going to show the work right over here on this side. So this is going to be finding A inverse. Okay, well, to find the inverse of a matrix, first we have to find its determinant. So the determinant of A is going to equal, remember the determinant is the main diagonal multiplied together, so 2 times 1, minus the other diagonal multiplied together, 3 times -1. So that's going to be 2 minus -3, which would give us 5. So the determinant of matrix A is 5. And since the determinant is not 0, A does in fact have an inverse. Now let's go about finding that inverse. So from the previous video, A inverse is going to be 1 divided by the determinant of A times the matrix where we switch the positions of the main diagonal. So we'll have 1, 2 instead of 2 and 1. And then for the numbers on the off diagonal, we're going to change the signs. We'll have a -3 and a +1. Okay, so we have 1, -3, 1, 2. Continuing, we found that the determinant of matrix A was a 5, so we're going to take 1/5 as a scalar and multiply it to 1, -3, 1, 2. Distributing that 1/5, we're going to get 1/5, -3/5, 1/5, and 2/5. So this is our A inverse. Okay, this is A inverse. So to calculate the variable matrix X, that's going to be A inverse, which we just found to be 1/5, -3/5, 1/5, 2/5, times -17, -4, because that's B, the constant matrix. Multiplying those together, we would get -1, -5, and this would be our solution. And notice that means that -1 would be the X value, -5 would be the Y value. Okay? So that's how we can use inverses, multiplicative inverses, to solve a matrix equation like that. Now let's look at the one from previously. At the very beginning of the notes, we had that system with 3 unknown variables, and instead of solving this one by hand, I'm going to show you how we can use technology to solve this system. So first things first, let's go ahead and write this out as the coefficient matrix times the variable matrix is equal to the constant matrix. So let's see, our coefficient matrix, that's going to be, for the top row, 1, -4, 3. For the second row, -1, 3, -1. And for the bottom row, 2. Notice that there is no y here, so it'd be a 0y. So it'd be 2, 0, then -4. For the variable matrix, notice we're going in order x, y, z. And our constant matrix, again, notice all of our constants have already been separated and put onto the right side of the equation for the system. So the constant matrix will be 5, -3, and 6. Okay, and once again, this is A times X equals B. So what we're going to do, remember, we're trying to solve for the variable matrix X, and we know that X will be equal to A inverse multiplied on the left side times B. So let's go over to our Desmos matrix calculator to calculate this. Okay, so here's our Desmos matrix calculator. First things first, let's plug in matrix A, which is a 3 by 3, and it has 1, -4, 3. Moving to the second row, -1, 3, -1. And moving to the third row, 2, 0, -4. I'm going to hit the enter blue arrow, that way it stores the matrix A. And now we also want to store the matrix B, which is our constant matrix. So I'm going to hit new matrix again. Matrix B is a 3 by 1, 3 rows, 1 column. And it is the matrix 5, -3, and 6. Hit enter to store the matrix. And now all we have to do to solve for that variable matrix X is A inverse times B, with A inverse being on the left side. So A inverse times B, and notice that we get the matrix 7, 2, 2. And this is our variable matrix X, where 7 is the X value, 2 is the Y value, and 2 is also the Z value.